Okay, this is Dr. Brown. Today we're going to look at the second video in our series of Calculus in a Nutshell, and we're going to be talking about looking at limits. How do you calculate limits? First of all, we see the notation, the limit of f of x as x approaches c. What does this expression mean? What it means in sort of a nutshell, in a simplified way, is that as x gets closer to the number c, then the function f of x gets closer to L. The limit of the function is said to equal L. So how do we calculate limits like the limit of the function f of x as x approaches c equal L? Well, very often, in fact, for many functions, we just simply plug in x equals c. So the limit of f of x as x approaches c equals f at c. So some examples. The limit of the function x cubed minus 2x as x approaches 2. We just plug in, and by the way, this is really two functions. The first function is x cubed, the second function is minus 2x. But one of the things we know about limits is that if you add or subtract the limits of different functions, it's equal to the adding or subtracting the individual limits. But anyway, here we're going to plug in 2. So we get 2 cubed minus 2 times 2 equals 8 minus 4 equals 4. So the limit is 4. Another example. Suppose a function is sine of x, and we want to take the limit as x approaches pi over 2. And here we just simply plug in pi over 2 for x, and we get sine of pi over 2. And if you folks ought to remember a good bit of trig, because we're going to use a lot of it this semester, sine of pi over 2 is 1. So there are all kinds of instances where you just plug in x equals c, calculate f of c, and you've got the limit. However, in many important cases, plugging in does not work. For instance, you will recall that we said for if s of t is position, that the derivative of the position, also called the instantaneous rate of change of the position, is equal to the limit as h approaches 0 of s of t plus h minus s of t divided by h. If you plug in fact, I'm going to plug it in up here. We get s prime of t equals s of t. That's what you get when you plug in h equals 0. You get s of t minus s of t divided by plugging in h equals 0, and we get 0 over 0, which is not defined. Now, so how do we deal with cases like this? Well, let's consider an example. Sometimes you may be able to cancel common factors to avoid the issue of dividing by 0. In other words, common factors in the denominator or the numerator. Let's take an example. The limit as x approaches 1 of x squared minus 1 divided by x minus 1. If you plug in, you get 0 over 0. But notice that we can write this as a limit as x approaches 1 of x plus 1 times x minus 1 divided by x minus 1. And notice we have common factors in the numerator and denominator. So this would equal the limit as x approaches 1 of x plus 1, and now we can plug in and we get the limit is 2. Now if you plotted this function over on the right, you would have, first of all, the function is undefined at x equal 1. So we're going to put a hole in it. But everywhere else, the function looks like a straight line, just like this. And you can see that as you come down from the right or from the left, the function is getting closer and closer to 2. However, f at x equal 1 is not defined. It's not defined. But the limit as x approaches 1 is definitely 2. You can get just as close to x equal 1 as you want to, and the value of the function gets just as close to 2 as you want to. So let's do another example. Suppose we had the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. Well, you plug in, you're going to be dividing by 0, but notice that this is equal to the limit as x approaches 2 of x minus 2 x plus 3. So now you got to remember how to factor. And notice, lo and behold, we've got factor in the numerator and denominator that are the same. We can cancel that out, and now we can just plug in x equal 2, and we get that this limit is equal to 5. And so anytime you can cancel out common factors and eliminate the 0, that's a way to go. Another possibility is to use a common factor. Not use a common factor, but use a clever strategy to manipulate the math expression. And in many cases, a radical expression may be simplified by multiplying numerator and denominator by its radical conjugate. So take an example. I want to find the limit as x approaches 0 of the square root of x squared plus 100 minus 10 over x squared. Now plug in x equals 0 and you're dividing by 0. In fact, if you plug in 0, you get the square root of 100 minus 10, which is 0, and you get 0 over 0 if you plug in. However, we can write this as the limit as x approaches 0 of the square root of x squared plus 100 minus 10 divided by x squared. Now I'm going to put the numerator in parentheses and multiply the numerator and denominator by the same number, which I call the conjugate, the radical conjugate of the numerator, which is going to be the square root of x squared plus 100 plus 10. If I do that, we got to do the same thing to the denominator, and I get x squared plus 100 plus 10. And notice, if you multiply the numerator out, you'll get the radical times a radical, and that will equal x squared plus 100. Then you get the outside, which will be 10 square roots of x squared plus 100. Then the inside is minus 10 square roots of x squared plus 100. And then the last term is minus 100. And that's all divided by x squared times the square root of x squared plus 100 plus 10. And notice that we can have fun canceling out the plus 100 and the minus 100, as well as the plus 10 times a radical minus 10 times a radical. And we're left with x squared in the denominator that cancels with x squared in the numerator, and we get the limit as x approaches 0 of 1 divided by the square root of x squared plus 100 plus 10. So when you plug in x equals 0, you get 1 over the square root of 100 plus 10. That's equal 1 over 10 plus 10 is equal to 1/20. So now by doing a clever manipulation, multiplying the numerator and the denominator by the what I call a radical conjugate. Of this case, the numerator, we get a cancellation of the problem of dividing by 0, and we now plug in and we get 1/20. Now I'm going to work one more example. Suppose we want to take the limit of x minus 9 over the square root of x minus 3 as x approaches 9. Now plugging in, you can see that you get 0 over 0, but using the same strategy of multiplying the numerator by the radical conjugate, which is the square root of x plus 3, and multiply the denominator by the same thing, we then get the limit as x approaches 9 of x minus 9 times the square root of x plus 3. Now the denominator becomes this x for the first term. Notice the outside and the inside will cancel, so and then the last term will be minus 9. So we get this for the denominator, and we can cancel the x minus 9, and now plug in x equal 9, and we get the square root of 9 plus 3 equal 6. So the limit is 6. Now, the fourth technique is to use a calculator to plug in a number very close to whatever C is. So let's take the example, and sometimes this will be a very handy way of doing it if you've got a very accurate calculator, and it will be accurate to many decimal places. The limit of x as x approaches 9 of x minus 9 over the square root of x minus 3. So let's plug in a number very close to 9. Let's plug in 9.001. If we do that, we get 9.001 minus 9 over the square root of 9.001 minus 3. And you can very clearly see that this is 0.001 in the numerator. And if you do this with your calculator, do it very carefully. And in fact, if you use parentheses, you could put the whole thing in your calculator all at once, and you get 0.001 over 0.001666237. Multiply that out and you get 6.00016667, and you conclude that the limit is probably 6 if you plugged in 9.0001 if your calculator was that accurate, then you would get a number even closer to 6. Now, we're going to talk a little bit about determining a limit from a graph that you might create or somebody else might create for you. Let's look at this first simple graph. We want to find the limit as x approaches x naught, and in this particular case the function is y equal x. So you can see just by going and looking at the graph, the limit must be x naught. The next graph is a constant function, y equal k, and you can see as x approaches x naught, in fact everywhere the function is equal to k. So the limit of a constant function as x approaches any x naught is equal to k. Now the next one looks like a sine wave, and we're asked to find the limit as x approaches c of f of x, and here we just simply go in at x equals c, see where it intersects the graph, and read it off the y-axis, and in this case we see it looks like the limit is 0.5. If we do this on test, I won't be trying to draw the graph crazy to try to confuse you. You should be able just to learn how to interpret this. Now, if you'll look at the functions here, the first graph is a discontinuous function defined piecewise. You can see on the left hand side it's 0, on the right hand side it's 1. There's a hole in the graph here. F of 0, because you have a heavy dot there, is equal to 1. Now, however, the limit on the right looks like 1. The limit on the left looks like it's going to 0. Since the right hand side and the left hand side don't agree, the limit does not exist. Now let's look at another function. I know you've seen it, and by the way, it's good for you to have your graphing calculator here in the classroom and whenever you're trying to work problems. This particular function has a vertical asymptote at x equals 0. In other words, it's not defined at x equals 0. It looks like the function is going up to infinity on the right and minus infinity on the left. So the limit of f of x approaches 0, does not exist. Now, you can make up all kinds of functions that may not have a limit at certain points. If you plug into your calculator sine of 1 over x for x more than 0, you will see that on the right hand side the function is moving up and down very rapidly as you get closer and closer to 0. If you zoom in, it never settles down so the limit does not exist. I would recommend that you plug this into your calculator and see for yourself that as you zoom in on x equals 0, that the function never settles down. Now, I'm going to tell you a little bit about the sine function. The sine function, as x approaches 0, the limit is always going to be x. In fact, the sine of anything, as anything in the argument of the sine gets smaller and smaller approaching 0, it's equal to anything. And let me illustrate that. If you graph the sine function on your calculator, be sure to put it in the radian mode, and then graph on the same screen the function y equal x, you will see that as you get closer and closer to x equals 0, that you can't distinguish between the sine function and the function y equal x. So if you zoom in, the sine function and the function y equal x look the same. Now, I am going to add another page here and do an example here. Let's look at the limit of sine of x divided by x as x approaches 0. Now we said that sine of x looks like x as x approaches 0, so we can write x divided by x, and we get x divided by x is 1, so the limit of sine of x over x as x approaches 0 equals 1. One more example and we'll have more on the practice quiz. If you take the limit of sine of 12x over x as x approaches 0. As x approaches 0, 12x is approaching 0, so this looks like the limit of 12x. Remember, the sine of anything approaches anything as x approaches, as anything approaches 0. So we get this, and notice we get the x's to cancel, and the limit is 12. Now we're going to very briefly define what we call one-sided limits. You've already got a taste of this when we looked at a function that had a discontinuity. Well, we have another function here. It's a step function. If we define the limit of f of x as x approaches 0, and we say we approach it from the right by putting 0 plus, looking at the graph, we get that it's equal to 1. If we look at the limit of f of x as x approaches 0 from the left, hopping on the graph and going in from the left, we see that the limit is -1. However, the limit of f of x as x approaches 0 without a plus or minus on it, in other words, the limit of f of x as x approaches 0, it does not exist because the right and the left hand limits do not agree. We can also say that the limit of f of x as x approaches c equals L has to imply that the limit of the function approaching c from the left and from the right must always agree. Now, we're going to look at sort of a crazy function here. You can see it's very discontinuous, and it's got holes in it here, here, and here. When I say it's got a hole in it, for instance here, the point 1 and 0 is not on the graph. Well, let's write down some things that we do know. First of all, f at 1 is equal to 1. That's because we see a heavy filled in dot there at 1 and 1. We can say that the limit of f of x as x approaches 1 from the left is equal to 0. We can say that the limit of f of x as x approaches 1 from the right, take a look at it, it's equals to 1. Notice that f at 2 is equal to 2. The limit of f of x as x approaches 2 from the right is equal to 1, and the limit of f of x as x approaches 2 from the left is also equal to 1. So here we can say that the limit of f of x as x approaches 2 from the right or left is equal to 1, so that limit does exist. The limit of f of x as x approaches 3 looks like it's 2 from the right or left. And finally, we can say that f of 4, you got to look where the heavy dot is, f of 4 must be about 0.4. Can't completely read that off. But the limit of f of x as x approaches 4 from the left is equal to 1. Notice that the function is not defined. You don't see any lines at all to the right of 4, so we can't say anything about approaching 4 from the right. Well, that is the end of this video on limits in a nutshell.